As an automatic evaluation metric, we use perplexity. Smaller perplexity for test data means models better generalization performance since it corresponds to log average or inverse probability. We examined the performance on multiple number of hidden states. Experiments are conducted with 3 different random seeds. In addition to the Neural Hidden Markov Model and Semi-Makov Model, we implement a baseline model that represents the initial, transition, and emission and duration probabilities as simply runnable wet vector or matrices with softmax output layers. The baseline model is almost not neural, but a hidden Semi-Makov model tuned by the same gradient-based optimizer. We compare the proposed model with this baseline to see how efficient the elaborated neural network components works. Now, I'd like to show you the experimental results. This is the results of automatic evaluation by perplexity. Smaller perplexity means models better generalization performance. We can see that our proposed models considerably outperformed the baselines. We conducted ablation studies to see the effectiveness of the additional context. The results show that removing any additional context degraded the perplexity. Among the additional context, removing the observation representation by bit classes leads a significant drop. Since we do not employ material percentrons for the architecture or calculation of emission probability, but force a model to learn relationships between states and vocabularies directly, the information of low bit classes would help the learning. In the next few slides, we give a discussion about the findings from our qualitative analysis. Here, we focus on 8 state models. We can see code clusters in the emission distributions and code progression rules in state transitions. This is the emission distributions of the best scored proposed model. By looking at it, we can find code clusters that mainly consist of the codes on the diatonic scales. We found that 7 scores and passing codes are merged into appropriate clusters. For example, looking at state 7, we can see the state consists of G measure code, G measure 7th code, and passing tone around G measure. On the other hand, the evaluation perplexity of the baseline model is worse than the Neural Hidden Markov Model. The best baseline model has more miscellaneous clusters than proposed models. However, we can observe that codes in the same tonality would tend to be merged into the same category in the baseline hidden Semi-Makov model. For example, G measure code and D measure code are in the same cluster. Next, I will show the findings from state transitions. Although we trained models without distinction between major and minor pieces, we can observe that obtained state transitions reflect the difference of tonalities. We counted the number of transitions after decoding the sequence of hidden states by the Viterbi algorithm, since the transition probability changes by context. The figure shows the count of state transitions on major pieces. We can see the tendency that state 2 or state 4 to state 7 to state 3. That corresponds to the transition from subdominant to dominant to tonic. Next, we show the state transitions on minor pieces. Here, we can observe a strong transition from state 5 to state 6, which corresponds to the transition from dominant to tonic. Unlike major pieces, the transition from state 2 to state 5 is increased, since it corresponds to the transition from subdominant to dominant in A minor. Finally, we show the state transition on Dorian pieces. Dorian is the first church mode and have no key signature, but the tonic of which is the D minor chord. Here, we observed the tendency that state 1 to state 2, which corresponds to dominant to tonic. We can see that the transition from state 7 no longer has the strong tendency of proceeding state 3, unlike C major and A minor pieces. Now, I'd like to summarize the main findings of this study. We presented a new method to obtain code boundaries, code categories, and code progression rules simultaneously by the Neural Hidden Semi-Makov Model. Secondly, experimental results satisfactorily showed the efficacy of additional context in terms of perplexity by comparing the baseline and conducting ablation studies. Lastly, in the best scored proposed model, we obtained clear code clusters to which the 7 codes and passing codes merged. In addition, acquired state transitions simulated the concept of tonic, dominant, and subdominant without consulting textbook. Thank you for your time and attention. Thank you very much.
Thanks very much, Yui, for that great presentation. We do have time for some questions. If you have a question, you can post it in the chat, or you can ask to unmute, and I can unmute you if you prefer to ask your question verbally. But we have one that's come in from BT Franklin. Can you see the question in the chat there?
Yes.
Would you like me to read it out? It's just so everyone can see the question. It says, very interesting research, thank you. Several questions. Okay, so we've got several. First question, did your findings deviate substantially from the typical assumptions of existing music theory or confirm those assumptions?
I think our method simulated the concept of tonic and dominant and subdominant well in the in the dataset we used, but we are interested in in our future work. I want to try to use more complex musics and find the concepts that not how to say yeah.
That's okay. Maybe if we move on to the second part of the question.
Yeah.
It's basically it's asking, have you tried or done any other investigations on different corpora? So you trained the system on the Bach chorales, but have you looked at training it on some other music or analyzing some other music?
No, we haven't, but in future, we'd like to try new corpus.
Do you have any idea about what that corpus might be? Will it be more Bach, or will you try?
Yes, I want to try our method for post-romantic era's music, and also more metrically complex musics such as organ works. And
Right. Okay. Thank you.